Hi, my name is Priyanka Nanayakara, and I'm a PhD candidate at Northwestern University. I'll present our work Measure, Observe, Remeasure, an interactive paradigm for differentially private exploratory analysis. In this work, our goal is to support data analysts in efficiently spending epsilon during exploratory analysis. To begin, imagine an analyst who wishes to conduct an exploratory analysis of some sensitive data, which are managed by a data curator. They may have some high-level analysis goals, but they don't know their queries in advance. Rather, they develop and refine queries as they learn more about the data. Second, queries may have varying levels of importance to their analysis. Now, because the data are sensitive, the curator only gives the analyst access under differential privacy. Under differential privacy, statistical noise is injected into computations to obscure each individual's information. The amount of noise is calibrated by a parameter epsilon, also called the privacy loss budget. The analyst must specify how much epsilon to spend with each query. Because epsilon controls the amount of noise, it also controls the expected accuracy of the noisy estimate returned. The curator gives the analyst a total amount of epsilon to spend during their analysis, and once the analyst spends all of their budget, they may no longer issue queries to the database. So how would an analyst decide how much epsilon to spend on each query? We'll first look at what happens in the current paradigm, then I'll introduce our proposed paradigm. The current paradigm follows a measure-observe pattern, where an analyst first issues a query with an initial amount of epsilon. Then they observe whether errors associated with the estimate seem too large. The bar heights reflect the noisy estimate, while the error bars reflect expected root mean squared error computed in a data-independent way. To make this concrete, imagine an analyst issues a query about the number of people in different age groups. If errors for each count are too large, it may be hard to distinguish which groups have the highest counts. So to get better accuracy, the analyst issues the query again, except this time they spend an increased amount of epsilon. If the errors still seem too large, they'll repeat the process with an even larger epsilon. Imagine this pattern many times, and it's easy to see how analysts can quickly burn through their budget before meeting their analysis goals. The measure-observe paradigm is designed under the assumption that queries are known in advance. While there are mechanisms that reuse information across queries and can lead to more efficient uses of epsilon, there's still a tension when we consider exploratory analysis, because by definition we cannot know all queries in advance. So how might analysts efficiently spend epsilon when queries are not known in advance? Our answer is in our proposed paradigm. Measure, observe, remeasure. In this paradigm, the analyst interactively spends epsilon so that no epsilon is wasted. First, the analyst measures a query with an initial amount of epsilon. Then they observe estimates to judge whether errors seem small enough in light of their higher level goal. If they feel they need more precision, they can remeasure, applying more epsilon to the query. On the back end, measurements are combined, so the analyst is always shown a new estimate with lower expected error. They can engage in the observe-remeasure loop as long as they still have remaining budget. To make the paradigm usable by analysts without differential privacy expertise, we instantiated it in an interactive visualization interface. On the back end, we use the high-dimensional matrix mechanism, HDMM, and the Laplace mechanism for answering queries in the measure step. In the remeasure step, we get a fresh set of estimates using HDMM and weight previous measurements by the inverse of their variance. For this talk, we'll skip these details, but more information is in our paper. I'll now walk through the interface. Imagine an analyst is exploring some data to find out what demographic factors may be related to income level. Here we see counts of people by marital status and income. We see one query on the screen, but the analyst can scroll and see other queries that they've previously issued. The top of the interface contains a progress bar showing how many remeasures the analyst has spent. Each remeasure corresponds to a preset amount of epsilon decided by the data curator. At this point in their analysis, suppose the analyst wants to know whether there are more divorced people than widowed people in the dataset. Based on the errors shown, they're not sure, and they'd like better accuracy. They decide to remeasure the query by clicking the Remeasure button on the right. Now that they've remeasured, they get a fresh set of estimates which have been combined with prior estimates. We see that the error is reduced. The old errors are shown in light gray dotted lines beneath the new errors for easy comparison. Let's say they still aren't sure enough and decide to remeasure again. Now the analyst feels confident enough that there are more divorced people than widowed people in the dataset. Let's say that they now want to know whether, when filtering on people who make less than $100,000, there's still more divorced people than widowed people in the dataset. The two histograms are linked, so the analyst can click on income groups they want to filter the marital status visualization on. Here, the analyst has clicked on income groups less than $100,000, so the marital status visualization only shows people in the selected income groups. In theory, the measure, observe, remeasure paradigm can lead to gains in accuracy, since no amount of epsilon is wasted. However, when analysts use the paradigm in practice, human error can impact results. For example, analysts may struggle deciding how to allocate remeasures, in other words epsilon, across queries, or they may also struggle with using noisy estimates to form beliefs about the unnoised data. Therefore, we conducted an exploratory user study to understand how analysts may interact with the paradigm in practice and learn where their errors may stem from. Our study had 14 participants with quantitative data analysis experience, and they were not differential privacy experts. Naturally, there's flexibility in decisions an analyst can make while conducting an exploratory analysis under our paradigm. Namely, they can decide which queries to issue. However, it's difficult to compare performance across analysts or to a notion of best possible performance while allowing for such flexibility. And so for this reason, we designed an empirical setting in which participants answered a common set of analysis questions across predefined queries on 3 different datasets. They answered 4 analysis questions each on a census, medical, and education dataset. They could spend up to 6 remeasures on each dataset. Each remeasure corresponded to epsilon of 0.3. They could answer analysis questions within a dataset in any order they wished, and there were no restrictions on how they allocated remeasures. Furthermore, to make sure there was a common, well-incentivized notion of good performance for the task, we scored their answers in terms of how close they were to answers found using the unnoised data. Specifically, we scored answers using proper scoring rules, which dictated the payoff associated with better answers to a question. Participants were briefed on how they would be scored. By using proper scoring rules, we could better ensure that each participant was equally incentivized to maximize their score and consequently their bonus payoff. They could earn up to $2.50 per question, and therefore $10 per dataset. And so their goal was to allocate remeasures across queries in a way that helped maximize their bonus payoff. For each dataset, they answered a mix of quantitative and binary questions. Let's go through examples from the census dataset. For quantitative, how many people over 65 years old are widowed or divorced? Participants provided answers in terms of an interval that they were 95% confident contained the unnoised true answer. For binary, are there more than 327 people who have never been married and make less than $100,000? Participants provided answers in terms of the probability they believed the true answer was yes. That is, the answer based on the unnoised data. So how did participants do? To rigorously benchmark participants' performance, we use a rational agent framework based in statistical decision theory. This framework also allows us to decompose participants' observed payoff loss by source. The framework uses the notion of a rational Bayesian agent to quantify the maximum amount of information that can be learned from the noisy estimates and applied to the decision problem of forecasting the true value underlying the estimate, thus bounding the maximum achievable bonus by someone in the experiment. At a high level, we conceive of a rational agent who understands the experimental design and initially only knows the prior over possible ground truth answers. They're presented with the same set of study tasks as participants, perfectly perceive the noisy estimates, Bayesian update their prior, and submit the optimal response. We use the framework to devise tight lower and upper bounds on payoff, details of which are in our paper. Now our results. Here, we see participants lost 41% of the possible payoff attainable. But why did they lose payoff? To figure out how much they lost because of suboptimal remeasure allocation strategies, we imagine the rational agent completes the tasks using the same allocation strategies as participants. The rational agent's expected payoff represents a new benchmark, which we call R posterior same. The distance between upper bound and R posterior same shows how much payoff participants lost owing to suboptimal allocation strategies. We see that participants lost only 4% of the possible payoff attainable due to suboptimal allocation strategies. The remaining loss is due to participants not being exposed to the full experimental design, not perfectly perceiving presented information, and not Bayesian updating. Participants lost 37% of possible payoff attainable due to these sources, which we call reporting loss. Thus, participants' payoff loss seems to be driven more by their inability to access information and form beliefs about the true data versus to allocating remeasures. In our paper, we introduce a series of other benchmarks that allow us to answer other more fine-grained questions about participants' performance. However, for now, I'll end with some takeaways. In this work, we propose the measure, observe, remeasure paradigm for exploratory analysis under differential privacy. We instantiated the paradigm in an interactive visualization interface and conducted an exploratory user study to see how analysts might use the paradigm in practice. Our study suggests that our paradigm may help analysts spend epsilon more efficiently by allowing them to interactively spend epsilon so they don't have to make high-stakes, one-shot guesses about how much epsilon to allocate to a query. As future work, we think it would be worthwhile to conduct larger studies which would allow for further disambiguating sources of error. We might also explore how analysts use the paradigm when they're allowed to set how much epsilon is allocated per remeasure and when they can pick queries themselves. Finally, our adoption of a rational agent framework to the differential privacy setting can be used to evaluate other differential privacy interfaces, which would allow the community to more rapidly identify where interfaces can be improved to support analysts in making more optimal decisions. With that, I'll end. We look forward to your comments and questions, and we can be reached online.